like a hairball just made out of one long strand of hair, and it's just taped to a sheet of paper. And what I'm about to do with the computer is I'm going to just pinch that hairball at just one little place on the hair, and I'm going to just tease out that one little piece of hair, and I'm just going to move it to a new location, a new random place. And if that move makes the hairball look a little bit more like Dan on the left, then I'm going to keep that move. I'm going to leave that. But if that move makes it look less like Dan, then I'm going to take the move back probably and try something else. And I'm going to do this over and over and over again. And after I do this 10 million times, it looks like this. So that's kind of neat. But the reason I'm showing you this is because this is basically how all machine learning works today. Now, there are some technical details, I'll grant you. We don't always use one long curve. Sometimes we use lots of little curves. And after we fit those curves, sometimes we use other curves to fit the first curves with layers. And we've got better ways than just randomly to move things around sometimes. But basically, those are engineering enhancements. At the end of the day, the system didn't know anything before it met Dan, before it saw his face. All it was a curve, a way of moving a curve, and a way of comparing the result to Dan, to the target data set. That's it. So is this really enough to build intelligence? Is this how we're going to build the intelligent machines of the future? Just wiggly curves? It's pretty good. It makes a cool picture of Dan. It's powering most of those startups that I showed you. But I do think there's something critically important missing here. I'd like to explain that to you with another example. So here, this is work that I did with Jake Neely. So here's a new target data set. Instead of Dan's face, let's do something even easier. Let's fit this red curve. Should be real easy. We've got a whole hairball. We can fit a line. That's easier than a face. But this isn't just any curve. This is data that was collected by Tycho Brahe between the years 1582 and 1600. Every night for 18 years, he went outside and he observed the position of Mars in the night sky. Mars moves around in the sky. Sometimes it's up, sometimes it's down, sometimes you can't see it at all. By some accounts, Tycho Brahe spent 10% of the GDP of Denmark to build the astronomical instruments that he used to take these observations. And they were more careful, more accurate observations than anyone else had ever achieved before. So accurate, in fact, that they enabled Johannes Kepler to, for the first time, write down a detailed structure of our solar system. Then, as now, data quality was an important issue. So you could ask yourself, as Johannes Kepler did, what is the structure of the solar system, the architecture, that could be producing a curve like this? How could we fit it? Well, let's call that structure, that architecture, let's call it the story of the solar system. So back in Aristotle's day, the story of the solar system was different. The Earth was at the center of the solar system. We don't believe that today. Mars went around the Earth. The sun went around the Earth. They went around in circles. And what we can do with that story is we can do hairball-like moves on it. We can kind of, pick the diameter of the Earth's orbit or Mars's orbit, and we can adjust it. We can pick it up and make a random move. Or we could take the velocity of the sun and give it a little kick. We can adjust it. And you can see that as we adjust the solar system story, the black line that Tycho Brahe should have observed, that's what the story predicts, is different than the red line, which is what Tycho Brahe actually saw. In particular, the black line sort of picks up the fact that Mars goes up and down, but there's little extra wiggles in there, and that's called retrograde motion, and people worried about that. And so Ptolemy came up with a different story. And he said, well, there's an invisible point, and that goes, the Earth's still in the center of the solar system, but there's this invisible point, and that goes around the Earth, and then Mars goes around the invisible point, and there could be more invisible points, and those are called epicycles. And we can do the same thing. We can do hairball moves, so we can change the radii and the velocities, and we can kind of fit it. And you can see it makes a new black wiggly curve. Looks a little better, maybe. It's got sort of retrograde wiggle motion in it. But let's really measure that. So let's sort of subtract the red line from the black line for both of these stories. Let's call that the error, the difference in the prediction of the story from the observed data, just like we compared the hairball to Dan. Just what's the difference? And you can see in Aristotle's story, the error is going down. And in Ptolemy's story with epicycles, it doesn't go down. It kind of stays pretty much the same. In fact, Ptolemy's story was not a step forward for science. But then